Hi everybody. Today I thought we'd have a look at part 2 of this project on the electronic DC load, where we're going to make a number of changes and improvements and additions to this project, which I'll go through shortly. The printed circuit board will remain the same, so those of you that are following this project and are building the project with the PCB, no worries there. We'll keep the main printed circuit board exactly the same. We may make some changes to component values as we progress, but that won't affect the overall position with the PCB. Now, before we go and have a look at some of the changes that we've made, I just want to make a point about the circuit diagram for this project. It was brought up by Phil, one of my viewers, about some resistor values. For some reason, when I uploaded the zip file that had the schematic diagram for this project, I also included two circuit diagrams. One file was labelled schematic and the other file was labelled circuit. The schematic file was the earlier prototype of this, and the circuit, the one that's labelled circuit at the end, has got the actual values that we're using on this project. And those differences are mainly to do with the divide by 10 resistor network, where I used a 9.09k resistor and a 909 ohm resistor, those precision resistors. Previously, in the earlier version I had an 18k and a 2k. I went for the precision because it was more accurate. And also the op amp in the feedback loop, where we measure the voltage across the 0.1 ohm resistor to measure the current flowing through the load. Those resistors that set the gain of that op amp, the 82k, which was on the early prototype, was later changed to an 8.2k. So look at the circuit diagram that's labelled circuit rather than the one that's labelled schematic, and you'll be fine. So let's have a look at the changes and the additions and improvements that I've made to the project today. Right, well, let's have a look at the changes that we've now made in part 2 of this project. I'll just quickly run down them for you. The first change that I've made is I've made some changes to the way the LCD displays the information, and in fact this will become apparent as we progress through part 2 of this project, so I'll cover that a little bit later. The next thing I've done is I've changed the way that the current and the power is set when we set the required levels. If you remember, initially we set these in milliamps and milliwatts, but I found that as I was going up in power, certainly with the wattage, this wasn't really suitable, so I've changed these now to display the readings as we set them in amps and watts, but I've done it to 3 decimal places. The next thing I've done here is I've added some safety feature for this particular project, which limits the current and the wattage exceeding preset levels. This is done in software, and because it's done in software in terms of the variables, as I'll show you later, we can change these to suit our particular needs. So that's another change that we've made. Now, during the previous part of this project, and certainly all the comments that came back, quite a few people were saying, could we add another function onto this that gives it the ability to measure the capacity of LiPo, lithium batteries. And I was actually thinking of this myself, so what I've done now in part 2 is include that as an extra feature. So we will be measuring the capacity of LiPo batteries over time and show the result in milliampere hours, and again I'll cover that in more detail shortly. Now, the other thing I've decided to do is change the Mosfet. The Mosfet we had in part 1 of this project did work fine, but I found that as I was increasing the power and certainly the voltage as well, I had a few issues at certainly the higher power levels where the Mosfet could become unstable and could actually blow. So I've changed the Mosfet to a different type now. I'm using the BUK 956R1 by NXP, and again I'll show you a little bit more detail of that a bit later on in this part 2. Now finally, the software version for the project has been totally upgraded now. I've added in all these extra features and changes that I've made, also made some other improvements in the software, and again I'll go through a little bit of that a little bit later on as we progress through part 2. So they're the main changes that we've made to this project, and let's now have a look in a little bit more detail as we go down the changes that I've made. Now we're going to have a look at the LCD display and the changes I've made on the arrangements on that now. So I'm going to start up the sequence. So if I power on, so you get the welcome screen again, and this time we're indicating we've got version 2 of the software. And now what happens is that immediately after the intro screen, the LCD shows it in constant current mode with the load switched off. And you'll notice here I've now got the DC load off at the top, and then we're now putting the actual current, actual voltage and wattage on the second row this time, and on the third row is where we set the current or the wattage or the resistance. And on the right hand side there you've got the mode, which is CC for constant current, and at the top there we've got the temperature of the heatsink, 18 degrees C. Now the other thing I've done is that when we now use the rotary encoder to select the or set the current, you'll see at the moment it's indicating on the first 0, but what I've done in software, I've limited the maximum current for the moment to 5 amps. So even if I rotate the encoder, you can see the highest number I can get there is 5 amp. If I keep turning it, I can't get any higher than 5 amp, but I can turn it back again. Constant current mode, I'm going to switch the load on. So the load is now switched on, and we're drawing just over an amp. And I'm going to show you what happens now if I select another mode. So let me go into constant power. And if we now select another mode from constant current or constant resistance, you'll see not only does it switch over to constant power, it automatically switches the load off. And that was one of the points that was raised in some of the comments I had with regard to part 1 of this project. So now switching mode, at the same time switches the load off, so you have to then switch the load back on again. Right, well I'm now going to demonstrate the power limit feature we now have on this DC load. It's set in the constant current mode at the moment. I've got the starting current set for 1 amp. The load is currently off, so I'm going to switch the load on in a second. I've got 15 volts going into this, and I want you to monitor the wattage and the temperature there as I increase the current and the load wattage goes up. So I've set the software at the moment so when we get in excess of 50 watts it should cut out, so it switches off the load and we'll get a power limit indication on the display. So let me just increment that. So I'll take it up to, I'll switch the load on first. So I'll switch the load on, you can see, so I'll switch the load on and you can see that we've got 1 amp being drawn now. That's 15 watts of power. The temperature you can see on the heatsink is currently 25 degrees C. I'm now going to step up the current from 1 amp to 2 amp. So I've now got 2 amps at virtually 15 volts. So that's giving us nearly 30 watts at the moment. You can see the temperature there going up now to 27 degrees. I'm now going to step it up to 3 amps. And 3 amps now at around 15 volts is giving us, well, it's giving us 44, just over 44 watts there. So I'm going to just move the cursor down into the milliamp region, and I'm going to increment it slowly and go up towards 50. So we're now at 47. So we're now at 49 watts. You can see the temperature there, it's 31 degrees C now on the heatsink. That's at 49 watts. I'll step it up now towards 50 watts. Right, and I just exceeded 50 watts there, and you can see what's happened now is that the load has been disconnected and there's an indication on the bottom of the display that says exceeded power limit. And now to reset that you have to simply just press the one of the function buttons again, either the constant current or any of the others. And if I press the constant current button again, we go back to the start position. So that's just a little safety feature which we can set. I've set mine to 50 watts at the moment to err on the side of caution, but theoretically we should be able to go up to about 90 watts I haven't tested it that high yet, but I've let it run at 50 watts, and the temperature on the heatsink goes up to around about 35-37 degrees C. The new Mosfet we're now using on this project, I just want to quickly have a look at the datasheet for that. Just some headline points really. First of all, is that the Mosfet itself is a true logic level Mosfet, which is quite good for our project. It's capable of operating up to 100 volts with a maximum current of 120 amp, and the junction temperature can go all the way up to a maximum of 175 degrees centigrade. So it's probably quite good for our project today as a DC load because of the constant current that's flowing through it. It will be getting hot over time. So what I want to do first of all is have a look at two of the key features from the datasheet just to illustrate my point. Well, one of the important graphs that you'll find in the datasheet is this particular one here, and this is the one that shows the safe operating area for the Mosfet, and we're interested in the DC area here, the DC range. So if you can draw a line from there down that DC line down to there, all of this is the safe operating area for the Mosfet. The other lines that you can see refer to if we're operating the Mosfet in pulse mode from 100 milliseconds up to there 10 microseconds. So let's concentrate in the DC area here so we can operate in that safe mode. And it goes on the bottom axis here is the voltage between drain and source. At that point there you've got 100 volts. I've shown here 30 volts, which I've marked in red, which is what we set out as one of our requirements for our DC load, and we also said that we would operate to a maximum of around 3 amps. So if we plot 3 amps against 30 volts, you can see that this sits quite nicely within the safe operating area of this particular Mosfet. The next thing we want to have a look at from the datasheet is this graph here, which shows you the mounting-based temperature of the Mosfet in degrees centigrade against a percentage of the total power capacity it can deliver. Now, according to the datasheet, it says that at 25 degrees C, around room temperature, this particular Mosfet can deliver a maximum of 349 watts. And that's what we can see here at the top of the graph. We go across there, that's 25 degrees C, and we can get 100% of what it says on the datasheet. But as the temperature of the Mosfet increases, if it gets down to, say, if it goes up to 50 degrees C, you can see that we're only then looking at around 80% of what the maximum value it could deliver in power. And if we go still higher, if we go, say, 100 degrees C, then the Mosfet now can only deliver 50% of the total power indicated on the datasheet. Just quickly want to have a look at some of the issues we're having with regard to the keeping the Mosfet cool and the heatsink. And in our particular project we set some parameters there. We said we wanted this DC load to have a maximum capability of 30 volts at 3 amps, and that equates to 30 times 3, which is 90 watts. That's the total capacity of the DC load, the maximum. So what we need to do is keep our Mosfet cool so it's operating safely at that maximum wattage if we go to that high. Now when we look at the particular Mosfet that we're using now, if you look at the datasheet, it tells you what the absolute maximum die temperature, that's the silicon chip itself, can be, and on the datasheet it says 175 degrees centigrade is the absolute maximum. So we need to keep it cool below that temperature. In order to do that we use a heatsink, but on the way to the heatsink we have all mechanical connections. This is called thermal resistance, and this will affect the cooling effect of that Mosfet. So what we're showing here is the thermal resistance of keeping that Mosfet cool, and the first thing we have is something called the junction to case. That's the die junction of the Mosfet to the case of the Mosfet, and if you look at the datasheet it gives you that in the datasheet as 0.43 degrees centigrade per watt. So if we multiply that by our 90 watts we'll get 38.7 degrees centigrade. The next thing we have is we have to connect the Mosfet to the heatsink, but on the way there we have a silicon pad isolating the Mosfet from the heatsink. So we have a silicon pad with some thermal grease or heatsink compound, and that itself has an effect in terms of thermal resistance. And we know, when I checked it for silicon pads, it has a thermal resistance of 1 degree centigrade per watt. Therefore, at 90 watts, it's 1 times 90, so we have 90 degrees centigrade there, which is the effects of the silicon pad. We now have the heatsink itself. I'm using an old one I salvaged from a computer with a fan on, and when I had a look at the data for that, in fact most of these type of computer heatsinks, they're 0.6 degrees C per watt. So whichever one you get from a computer, it's round about that sort of figure. Some will go a little bit lower, some a fraction higher, up to anything up to 0.8. But this one I'm using is 0.6. Multiplying that by our 90 watts, we get 54 degrees centigrade. If we assume that the average ambient temperature we're operating the device in is 25 degrees C, we need to add that on as well. So by adding all of these thermal resistance temperatures here, we get a total of 207.7 degrees centigrade. And you can see that that's far higher than the absolute maximum of 175 degrees C, which is specified for the die of the Mosfet chip. So that wouldn't work. At that sort of wattage power, you'll just blow the Mosfet. So you couldn't operate at those sort of power levels. And that's the issue I was having with the project as we had it in part one. One was the fact that I was using a Mosfet which is not as high a spec as the new one I'm going to use today. But secondly, the silicon pad was having a massive effect on the ability to keep the Mosfet cool below its absolute maximum die temperature. So I'm going to move away from that. So the next thing I thought was we could use a mica pad. So let's have a look at that. So I've now replaced the silicon pad with a mica pad between the heatsink and the base of the Mosfet, and that effect, if we look at the data for mica pads with silicon grease or heatsink compound, that gives a thermal resistance of 0.4% or thereabouts degrees C per watt. So if we multiply that by the 90 watts, you can see that's now dropped down to 36 degrees C. So if we now total these again, we now find that we have a total of 153.70 degrees centigrade, which is below the absolute maximum of the die of the chip. So that would be satisfactory, and that would work probably okay. But even so, we're still not too far below the absolute maximum. So it would be nice to get even lower still. So what we're going to do now is, instead of using either a silicon pad or a mica pad with heatsink compound, what we're going to do now is see what the effect would be if we simply bolt the Mosfet directly onto the heatsink and simply just use heatsink compound. So let's change that and have a look at that effect. So here we now see I've changed the connection of the Mosfet to the heatsink by simply bolting it directly onto the heatsink and just using heatsink compound, so direct contact. And this has a dramatic effect, because you can see here now that the thermal resistance of doing that goes down to 0.1 degree centigrade per watt. So if we now look across here, we can now see we've only got 9 degrees centigrade there. So if we add all them together again, we now get a final figure here of 126.7 degrees centigrade, and that is now well below the maximum die temperature of the Mosfet of 175 degrees C. So this simply illustrates that the best way of ensuring that the Mosfet doesn't overheat in our particular project is to simply bolt the Mosfet itself directly onto the heatsink and use some heatsink compound. And because we're only operating around 30 volts, I mean basically anything up to around 60 volts is not dangerous. You won't have any problems with that at all. So we're using low voltages anyway, so connecting it directly is not an issue in this case. If you were going up to 100 volts or more, obviously then you need some insulation between the Mosfet and the heatsink. But in our particular case, that doesn't matter. Here we now see I've mounted the new Mosfet I've chosen directly onto the heatsink, just simply using heatsink compound, bolted it tightly on there, and the cooling effect that I'm getting now is just far superior to what we had previously, and it's certainly keeping the Mosfet within its safe operating area. Now what we'll do next is we'll have a look at the additional circuitry I've included for the battery capacity function that we add into the project. And what I've decided to do is use a real-time clock IC rather than trying to use a timer within the Arduino. A number of reasons for that, but briefly, I will probably be looking at some other features later on in this project, so I wanted a real-time clock. And also this particular IC also has 1 kilobyte of EEPROM memory, which we can use later. So here we are. The particular real-time clock IC that I've chosen here is the MCP 79410. And the reason I chose that is that this particular IC has an I2C2 address of 6F, and that particular address doesn't clash with anything we've already used, whereas some of the other real-time clocks would. So a reason why I chose this particular IC. The chip itself is just a little 8-pin surface mount IC that will mount on a small PCB, and my intention is that we'll unplug the connections for the liquid crystal display, and this little board will then plug into that, and then there'll be some pins on this board that will then supply the LCD. So quickly looking at this IC, we've got pins 1 and 2 where we have the crystal and the capacitors there for the frequency of the clock. It uses a 32.768 kilohertz crystal, little watch crystal there. The important thing here is that you need to make sure that the crystal that you buy for this project, or for this IC really, has got a capacitance of between 6 to 9 PF. That's important. We then have a decoupling capacitor from the supply voltage on this chip, the 5 volt supply, a 0.1 microfarad or 100 nanofarad. And then the connections to the IC are simply these 4 here, plus 5 volts ground, and then the 2 lines for the data and the clock for the I2C bus. Now the other point is there's 2 pins here that I've left unconnected at the moment. There's possibility for a backup battery, which we don't need for this project, so the pin 3 of this is just left disconnected. And then there's also a multifunction pin on pin 7. What they say in the datasheet is that that could be simply left open if you're not using that function. This is for alarms or square wave output or whatever, but we're not using that feature, so we leave that disconnected. Just going back to the pin 3 for the backup battery there, it does actually say in the datasheet that if you're not using it, it's advisable to connect it up to the plus 5 volts. So we can have a look at doing that. I think on the little PCB that I've produced so far, that I didn't do that, but you can soon link it across if you need to, but it seems to work quite well with it left disconnected. Right, well, I think what we'll do now is we'll have a look at the components and the PCB I've put together for this additional little piece of the circuitry. Here we see all the components now for the additional PCB with the real-time clock on there. So I've produced a small PCB which will plug into the main PCB. And to do that we've got a connector there which we'll use to plug into the pins on the main PCB. And this angled pins here are what we then use to connect the liquid crystal display. There you can see the real-time clock IC. There's the decoupling capacitor, the 0.1, the 2 10PFs and the little clock crystal there. There's the transparency that we use for the make the PCB, and I'll make that available for you. And there's a battery holder there for the LiPo batteries which you can use as well. Here we have the little PCB now with all the components mounted. You see here the surface mount IC is soldered on the print side of the board. Pin 1 is just there, and there's a little dot on the PCB which indicates where pin 1 of the IC should go. So that's the orientation of the IC. And there's the connector there soldered on the print side of the board that will then plug into the socket on the board, the pins on the board that at the moment go into the LCD. Now the point I'll mention here is that you can see that I've had to solder this particular socket on the print side of the board, so you have to have a bit of a gap there, And what I found easier is if you get one of these connectors which has got longer pins on it, and you can cut it down to size, so we can cut 4 off of that, and then you can stand it off of the board a little bit and you can get your soldering iron in then to solder these connections on the print side of the board. I'll just turn the board around, we can have a look at the other side. So there's the top side of the PCB. So there you can see the crystal and the 2 capacitors, and there's the decoupling capacitor there from the supply line, and there's the angle pins there, and that's what's now going to connect to the liquid crystal display. Pin 1, I've just marked that with a little dot on the board, but pin 1 is that one there, which is the ground. So you just need to be careful when you plug the liquid crystal display in, that is ground, and then the next one is plus 5 volts, and then you've got data and clock. Right, we'll just have a look at the positioning of this new little PCB. I've unplugged the liquid crystal display from those 4 pins there, and the new little board now plugs into that, so the idea is that that will plug in there in that direction. So then we've got these pins here which are now going to feed the liquid crystal display. Here we now see I've plugged the liquid crystal display lead now into those 4 pins that we've got on the little real-time clock PCB board there. So that's the connections. Well, the next thing we're going to do is now we're just going to demonstrate the new feature of the battery capacity mode, which where we discharge the LiPo battery and measure its capacity in milliampere hours. So let me just demonstrate that to you. So we're going to use one of the spare buttons we had, and by selecting that, what you'll notice the change to the display. So let me just press the battery capacity button. So what you see now on the display is, you see at the top of the display we've got battery off indicating the load to the battery is switched off at the moment. We've still got the temperature there. The second line is still showing you the current, the voltage and the wattage, the actual readings. And then the next line is where we set the current for discharging the battery, the constant current. And what I've done in software is I've limited that to a maximum of 1 amp. So you can set the current anything from 1 amp downwards. And to the right of that you've got BC, which tells you it's in the battery capacity mode. Now at the bottom line there on the LCD we've got a timer in terms of hours, minutes and seconds, and then to the right of that we've got the figure which will indicate the battery capacity in milliampere hours. A LiPo battery will at least simulate that. So we've got, as you see there, we've got a voltage of 4.2 volts. I haven't set any current at the moment, and the load is still switched off. So the first thing I'm going to do is I'm going to set the current to 1 amp. So I'm going to just press the button on the rotary encoder to move the cursor over, and then just increase that to 1. You can't go any higher than 1 on this. If you try to go any higher, it stops you. It just stops at 1, no matter how you keep rotating the encoder. But you can go down from 1, so you can increment the decimal places, the milliamp places, if you wish. So the next thing I'm going to do now is I'm going to switch the load on. So we've now switched the load on. So there's now load on the battery. There's constant current load on the battery of 1 amp. So you'll see gradually as we discharge the battery, the voltage drops, and at the bottom of the display there you can see the timer running there, 18, 19, 20 seconds, and to the right of that it's now counting up the capacity of the battery in milliampere hours as we discharge. Now what we've done is I've set the stop limit for discharging at 3 volts. If it goes lower than 3 volts then it will stop discharging the battery and switch off the load, and the 3 volts is the normal cut-off position for LiPo batteries. So when it gets to just below 3 volts it cuts off, and it'll give you the final reading there, which will be the battery capacity reading. Now before I do that, what I want to do is show you another little feature here, is that you can halt the discharge rate. So if I press the the load on-off button and switch the load off, it holds the reading that we reached so far. So it stops the timer and it stops the milliampere hours increasing. So that's the drain that we've used so far. That's the capacity we've used so far of the battery. So I can then restart it again if I wanted to by pressing the load on button. So it continues where it left off. So we now let it run until the voltage drops below 3 volts, and at that point the load will be switched off, so that will go from on to off, and we'll get the final milliampere hours reading on the bottom of the screen. So I'm going to turn the voltage down just to simulate that now. So I'm taking the voltage down gradually. I'll just, so we're around about 3.2 volts there. It's still counting up. You can see that the timer still going, and you can see the milliampere hours also incrementing. So I'm now going to take it below the 3 volt threshold, and as I go below 3 volts you can see that the load is now cut off. It's at 2.99 volts. The load is now cut off, and we get the final battery capacity reading there. In this case it's 51 milliampere hours, and also the time that was used for that as well. So that's the new battery capacity function we have on the DC load. And then to reset it, you can press any of the function buttons. You can press the battery capacity button again and it goes back to the start, or you can press any of the other function buttons. If I press the constant current button, then it just goes back to a different mode. I just want to quickly show you underside of the main PCB. What I've done there is that the track that's going from the source of the Mosfet to the 0.1 ohm current sense resistor there, I've filled that track with solder to give it more thickness, so that helps with the higher current. So I would recommend you do that, or alternatively you can solder a thick wire from the source of the Mosfet to the top of the 0.1 ohm resistor, but you need to make that track thicker to handle the higher currents. You'll also notice that I've soldered the leads going to the connection for the load directly as close as possible to the drain of the Mosfet there, the red lead, and the black lead, the earth return there, I've soldered directly onto the other end, the earth return end of the 0.1 ohm resistor. And the wire I'm using there at the moment is 14 gauge wire. Since we've added the extra feature, I just want to recap on the connections to the push buttons, because we now have the battery capacity option there. So here we see all the push buttons, and that's going to data pin 10 of the Nano. The constant power is data pin 9, the constant resistance is data pin 8, constant current 7. The load on off toggle is going to data pin D6, and then the cursor position push button, which is on the that's the button that's on the rotary encoder, is going to D5. So just a quick recap so you know exactly which pins are going to which button. Right, we'll just have a quick look at the software for this project. I'm not going to go through all of it today, but I just wanted to point out a couple of things. First of all, at the start of the software you can see all the libraries that we've included, and where I mentioned a liquid crystal library or the DAC library there, the MCP 4725, or the ADC library there, which is for the MCP 342X there, I'll give you all the links where you can download those libraries from. They'll be in the comments next to the library itself on the software. And the other thing we've done also is I've included a new library there now, which is the library for the MCP 79410, and that's the real-time clock. This is a library that I produced with the help of my eldest son Andrew, because we wanted a particular features on that real-time clock to use it as a timer in this particular DC load. So we rewrote the library for that to fit our needs, and I'll make that available as a download for you, and I'll put that as a link below. Now I just want to show you a couple of a few variables at the start of the software, just to identify it, and I've just highlighted it on this printout here in red. The variable there that we've got, battery cutoff volts, which is a float, that's set at 3 volts. That is for the LiPo battery. That's the cutoff point when it stops discharging the battery, so that's where that is set. And below that you'll see there's another variable there called the maximum battery current. That's set at 1, that's 1 amp. So we've set the maximum current. You can set the discharge rate out there at 1 amp, but you could change that if you wanted to. Also you could change the 3 volts if you felt you needed to. Another couple of variables you'll find in at the start of the software, I've highlighted here again in red for the moment. That's the power cutoff. That's set at 30 there, but I just increased mine to 50 watts. So that's where you set the power limit when the excess limit cuts in. And as I say, I've altered the software now, so that is reading 50 watts. This one is saying 30 watts, but you can select whatever wattage you want as your power limit within reason, and you just put it in that variable there. And then directly below that you've got the current cutoff. That's the maximum current we can set the set current to, and at the moment I've set that at 5 amps. So, but again, that can be changed as needs require and as we progress with the project. So there's 2 variables there that we can adjust to our own needs. Well, I hope you found part 2 of this project on the DC load of interest. As usual, I will put some links down below where you can download the latest version of the software for this project, together with the library, the new library you'll need for the timer. I'll make that available as a zip file. There'll also be another zip file where I'll include the artwork for the little PCB and the schematic for that, and any other information you may need for this project. I'll probably put also a parts list there. I've been asked by a few people if I can give a bill of materials, so I will put a parts list as a download below as well. So I'll leave it there for today. In part 3 of this project we'll progress further and look at making a few more changes. I'm trying to maintain the same hardware, and what we'll do probably in part 3 is have a look at just using one button that rotates the different functions. That'll free up some spare buttons we can then use for other features. And we'll have a look at how we can improve the calibration as well, and do that in software. So there's a number of things that we can look forward to. Even the battery capacity function can be improved. I'd like to include a menu for different types of batteries, so not only LiPo batteries, but also we could look at NiCad batteries as well, and any other type of battery. So I'll add that as a to-do list for part 3 of this project. So if you found this of interest, please give me a thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.